So if you're like me, you might have known growing up this kind of general concept of a galaxy, that the star, that our sun is a star, maybe you knew that, and that it is a member of a galaxy of stars we call the Milky Way galaxy, and we knew that there are other galaxies out there, but it wasn't actually until 1923 or so that scientists actually kind of proved the fact that there are these way far away objects called galaxies of stars. So distance was an important player in that. So just to kind of remind you that distance can be kind of deceiving at times. For instance, we use what we call the inverse square law to basically say that that the brightness of an object will vary the inverse of its distance squared to us. So for instance, we have the apparent brightness of these two objects, a candle and a lighthouse, looks the same to us, and that's only because the lighthouse is so very far from us. So I'm going to kind of talk you through a few ways of measuring distances, and they're called like step 1, step 2, step 3, step 4, step 5, step 6, I think. And each step it's gauging the distance to a celestial object, or measuring the distance to a celestial object that's even farther away. So for instance, and I think I'm going to kind of show you this concept of using radar. Okay, for instance, we could, if we sent out, I'll kind of look at celestial objects here in a minute, but one thing about radar is that, for instance, I kind of giggle because I think it's not fair to use radar to find fish, but you could. For instance, you see we're sending a signal down through the water, and we could kind of see if we have any sort of mountains down here, or some highlands down here on the floor of the water. I don't know if this is the ocean necessarily. And we can gauge that by how quickly the signal comes back. So for instance, look where my mouse is. If I put a big fish here, it would return faster, wouldn't it? And so the time it takes for a signal to come back is like using radar. And so using that to find the distance to celestial objects, for instance, we could send a beam of light to the sun. Okay, and you can kind of see the way this is it's got a cute little radar on the Earth, and I send something traveling at the speed of light to the sun, and I look for it to come back. And down here, actually, you can see the round trip. It took about 16.5 minutes. Now that might sound familiar because if you, the sun is located about 8 light minutes from us. So traveling at the speed of light, round trip would be about 16 minutes. So for instance, over here, this is a practical sort of thing. Here's Mars, and for instance, when we want to send a signal to Curiosity and look for Curiosity's reply, the time it takes to get that signal back is about 40 minutes from the time we sent it. So it's about 20 minutes one way and 20 minutes the other way. And we can use the time it takes for the signal to traveling at the speed of light to get to distance. Okay, so that's step 1. This actually radar sort of approach can only work for relatively nearby objects like planets. Okay, step 2, we said that although most stars look like they stay in constellation patterns, throughout the year, if a star is relatively nearby, we will actually see that star move against the background stars as the Earth orbits the sun. That's called parallax. And it depends on how good your telescope is to kind of see that subtle movement of that nearby star. But we say between 100 or 150 parsecs is kind of the limit of finding. We can actually find the distance to a star using parallax. So that is step 2. So in order to kind of set you up for step 3, I want to remind you what we saw a minute ago with the candle and the lighthouse. The fact that the lighthouse, the light from the lighthouse was diluted by I'll put this up here. The light from the lighthouse was diluted by 4 pi times the distance squared that the lighthouse is from us. And that is then that diluted down, and we saw it as a particular brightness. So then remember we talked about we can find the distance to stars if we know the luminosity, how much energy it should be putting out based upon its mass and the stage in its life, and its measured brightness. We can come up with the distance to that star. So that would be step 3. And actually we're going to use what we call a standard candle in this sort of technique of pushing it even further to basically gauge distances to galaxies. And it works very similar to this. There are certain stars that we know that just like, how do I say this? Just like stars that we know their luminosity because their main sequence and they have a certain mass, so we know their luminosity. So also there are other stars out there that we can use as standard candles. I'll show you that when we get to that. This actually is showing you kind of the influence of the distance of a set of stars. So it's using this approach where we're using the fact that the brightness is diminished by the fact that this set of stars is farther from us. So relative brightness, then, it would seem that this is Hyades cluster and the Pleiades clusters. These are both open clusters, and what we've done is kind of put them on a modified HR diagram. You might recognize this is kind of main sequence stars. And so the fact that the whole set of Hyades are generally have a brighter, are generally brighter, then that would mean that these are closer. Okay, speaking of Pleiades, here are the Pleiades, otherwise known as the Seven Sisters, in the constellation Taurus. It's like an open cluster. It could kind of qualify as a little asterism in a sense that maybe. Sometimes through binoculars, people say, oh, that looks like a little dipper, and they're right. So we can use this technique then of we'll know its luminosity. We compare its luminosity to its brightness and get to distance, basically, of that cluster of stars. So another standard candle that we use now is a specific type of star, a specific type of variable star called a Cepheid variable. Now we've talked about how stars can their brightness varies from our perspective. One way we said is you can have an eclipsing binary. But another way is if a star has left the main sequence and it's headed up to the giant or the supergiant stage, and it's in what we call this instability strip. And then it can kind of pulsate, basically, not like a pulsar, but it kind of gets brighter and then dimmer and then brighter and then dimmer. It's kind of a subtle thing, but if you know what to look for, you can see it. So for instance, when I mentioned it's a subtle thing, you can see this particular Cepheid variable star has left the main sequence. It's in that instability strip, and it gets brighter and dimmer and then brighter again over a period of 50 days. So that takes a little bit of patience. Okay, so we would say the period for that Cepheid variable star is 50 days. And then the cool thing, this is how we use it as a standard candle, is we can look at its period. For instance, instead of 50 days, here's a Cepheid variable with a 30-day period, and it corresponds to a luminosity of 10,000 times the luminosity of our sun. So that's what I mean by standard candle. Then we know that the amount of energy that star, that particular Cepheid variable, is pumping out is 10,000 lumen, or times the luminosity of our sun. So then if we compare its luminosity with its brightness, how bright it appears to us, we can get that kind of a dilution factor due to its distance. So this is a way we can judge the distance to this particular star. And as you can you see where this scatter plot now plots out notice the shorter the period, then the lower the luminosity. And the higher the period, the greater the luminosity of that Cepheid variable. So this is how we use them as standard candles. And we can use them to find the distance to Cepheid variables in our galaxy. And we're going to see that actually Hubble, and I just can't picture him doing this, but he did, looked at the Andromeda galaxy, and he tracked a Cepheid variable, a star in the Andromeda galaxy, and he could actually then, by its period, get to its luminosity and then compare it to its brightness and get to distance. Is that cool or what? Okay, so this would be step 4. We can use the Cepheid variable basically as a standard candle. Just keep in mind that the shorter the period of the Cepheid variable, the less the luminosity. The greater the period, the greater the luminosity. Isn't that cool? So leading up to kind of a spin-off of that, we can use when a white dwarf type 1a supernova goes, then it has a standard amount of luminosity. And so when that event happens in a distant galaxy, we can use that to, we know its luminosity then of the event, and we can compare that to its brightness and get distance to that galaxy. So here are some examples. The way, I think there's 3. So top and bottom, what you're looking at, in the top is the galaxy. I know it looks a little pixelated, but down here in the bottom is the galaxy plus a supernova event. Okay, galaxy, galaxy plus supernova, galaxy, galaxy plus supernova. This summer 2012 and fall 2012, I'm thinking we had a handful of supernova events that happened in galaxies. And I mean, well, you can see from these photos that they're not going to make our sky any brighter because they're not happening in our galaxy, but we can see them happening in other galaxies. Isn't that cool? So that would be another way of gauging distances to galaxies. So just to kind of then bring you up to speed, these next few slides talk a little bit about the whole, how did we finally figure out that those kind of wispy looking things up in the nighttime sky weren't just regular nebula, that they were actually galaxies of stars. And it was the distance factor that actually resolved the issue. So this is a photograph of, isn't this beautiful? A photograph of the Andromeda galaxy. And, you know, see, back in the 1920s, you know, I can see where they would look at this and it just kind of, it's either nebula or is that actually cloudy, those actually are individual stars. So here's Edwin Hubble looking through his telescope. And I think I've already kind of mentioned that he tracked a Cepheid variable in the Andromeda galaxy and came up with a period of that Cepheid variable, then used the scatter plot to come up with its luminosity of that Cepheid variable, compared it to the brightness, and voila, got the distance to that. Now we, at that time then, knew to be the Andromeda galaxy of stars. It's just, speaking of Edwin Hubble, let me go ahead and kind of set you up for yet another way that we can find distances to galaxies. And that's using what we've talked about earlier in this course, something called redshift. And we said that if an object is emitting radiation and that object is moving away from us, we said that the wavelength of the energy that object is emitting will look lengthened to us, okay, called a redshift. So this is how this works. The other thing is, remember we said that and we'll talk more about it in this chapter, that the universe is expanding. And we said that basically what that means is that all galaxies are moving away from each other. And along those lines, all galaxies are moving away from the Milky Way galaxy. So with this recessional motion then, we get redshift, and it looks something like this. So what we expect kind of a galaxy to maybe generally emit to us in this region of the electromagnetic spectrum. Remember, we've looked at these before. This is kind of like a light curve. Along the y-axis is brightness, and along the x-axis is different wavelengths. Okay, that's what we expect to see. Well, what we actually see is this whole thing shifted over to longer wavelengths. So pick a spot, and kind of this spot up here. Notice that it is supposed to be right here, but it's over here. I don't know if the whole thing is shifted over to the right. And specifically, this particular galaxy is showing a 5% redshift. And not only are galaxies moving away from us, but the galaxies that are further from us are moving away faster. And it's nothing personal against our galaxy. All galaxies are moving similarly to other galaxies. So basically, the more the redshift we see, then we know that that galaxy is farther from us. Does that make sense? So Edwin Hubble then, once he saw this sort of redshift in galaxies, he started plotting them on a scatter plot. And so what we see here basically is how far away that galaxy is from us, from the Earth, in megaparsecs, and then along the x-axis. And along the y-axis, we see how fast it is moving away from us. And I already said that the farther it is from us, I'll go ahead and play this little applet. I think this is so cute. I love the little telescope. Can you see the dome moving? So for instance, scatter plot. Pick this galaxy. This is M51. Looks like a pretty spiral, doesn't it? So let's go ahead and plot it. Put it down here on this graph. Let's pick another one. Oh, that looks like an elliptical. And notice it's up there. Scatter plot on its way. So for each of these, this would be painstaking, I think. He had to find the distance to the galaxy using a Cepheid variable or a supernova event. Okay, and then he had to find the redshift, using the redshift, find the recessional velocity. That's along the y-axis. So you can kind of see scatter plots are notorious for sometimes they don't look, they're scattery. And you're going to see some kind of noise, but what they saw, and let me go ahead and show you the whole thing. See that red line? You know, the cool thing, sorry, red line, I meant green line. The cool thing is that with a scatter plot, you can see a trend and then lay an approximate line through that trend, and that's that green line there. So again, with increasing distance from the Earth, or from our solar system, we see that the galaxy is moving faster from us. Okay, and that's called Hubble's law. So each of these dots here then represents a galaxy, kind of like you saw in the scatter plot before. Notice what's also drawn in here is, see these kind of two dashed lines on either side of the slope, the kind of the main red line. That's kind of showing you the wiggle in the relationship, the farther away the galaxy is from us. So you notice this H0. This is actually what we call Hubble's constant, and it definitely has a significance, and we'll talk about that in a slide coming up. Okay, but can you already see that that we can take the recessional velocity is equal to Hubble's constant, which is 22 kilometers per second per mega light years, times the distance. We can rearrange this to get distance. Okay, so just to kind of summarize, because this is another step, we can use redshift to get to velocity, recessional velocity, and we can use recessional velocity then to get to distance. So distance, all we got to do is take its recessional velocity divided by that 22. Pretty cool. And that kind of summarizes step 6. Distances of the farthest galaxies now are measured from these redshifts. So this is kind of a neat I think, a neat figure that looks at kind of the steps 1 through 6. So for instance, we said within our solar system, we could use radar. And then we said for nearby stars, we can use parallax. And then for far away stars, we can kind of use this main sequence fitting, which is basically we know the luminosity of stars or sets of stars as they are in the main sequence. And then we can compare that to their brightness as they appear. And then we talked about Cepheid variables, the fact that the period of their kind of pulsing, becoming bright and dim, actually we can get the luminosity from that. And then from luminosity, we again compare it to brightness to get distance. And then 2 more left there. We can use distant standards, such as white dwarfs or Cepheid variables, to get to the distance of a galaxy. And the last one is Hubble's law. And Hubble's law would be to use the redshift. The redshift to get velocity and velocity to get distance. So I think that's a pretty good summary. I mentioned that Hubble's law, H0, has some significance, and actually we can use H0 to get to one of several ways to estimate the ultimate age of the universe. And so what I've read is it's 13.7 billion years is about the beginnings of our universe. So if we take the 22 and keep your wits about you, actually if you take 1 over that 22, and I'm a firm believer in what they call the factor label method of working problems, you do get to 13.65 billion years. So